and it is the day 5 of the chapter Structure of Atom, double class. Okay, so welcome back, all of you. So, azimuthal quantum number. On your screen, I have written over there azimuthal quantum number. Now this azimuthal quantum number, it can have positive integral values between 0. It can have positive integral values between 0 to 0 and n minus 1. Okay, and this n stands for the principal quantum number. So there is a relationship which you must try to remember. Okay, so the values of L, azimuthal quantum number, lies between n minus 1 and 0, like this. It is greater than 0, it is less than equal to n minus 1. Greater than equal to 0, or so this relationship, if you remember, then you can easily figure out the different set of azimuthal quantum number values. Okay, now what are the information provided by the azimuthal quantum number? Let us discuss those point wise. Okay, so the first information which is provided to us by the azimuthal quantum number is the subshell, in which in which in which the electron lies. The subshell in which the electron lies. This is the first information provided to us by whom? By the azimuthal quantum number, which I have already told you in the morning class. Like, say, if there are values of L, 0, 1, 2, 3, and so on. So the subshell, the corresponding subshell is like this. The subshells will be, for L value 0, the subshell is S. For L value 1, the subshell is P. For L value 2, the subshell is D. For L value 3, the subshell is F. So this is the first information provided by the azimuthal quantum number. After that, next point number 2. The azimuthal quantum number tells us about the number of subshells present in a principal shell. So this is the second information provided by the azimuthal quantum number. That means if you know the value of the azimuthal quantum number, it is also going to tell you the number of subshells present in a principal shell. For example, let us see the possible combinations of N and L. Okay, suppose if I write down the principal shell, okay, for principal shell, I'll make this column. So I'll write down K principal shell, L, M, and then N. Now for the corresponding principal shell K, L, M, N, the value of N I will write down. Value of N I'll write down. Okay. For K it is 1, L it is 2, M it is 3, N it is 4. Similarly, correspondingly, the permissible values of L. Permissible values of L, azimuthal quantum number, for this principal shells. Let us see what are they. So for K shell, value of N is 1. So for the K shell, value of L will be 0. Okay. For N is equal to 2, the value of L will be two values, 1 and 0 and 1. For N is equal to 3, there will be three values, 0, 1, 2. I think you are getting the idea now. If you look at this previous slide, this is what I am doing over here. This is the relation I am following just now. Okay, to write the permissible values of L. And for the value of N, which is 4, the permissible values of L are 0, 1, 2, and 3. Now, Now the next column I will check and get the possible subshells. Possible subshells. Now the possible subshells for the values of L I'll get. When it is 0, this is S. Okay. When it is 0, it is S. When it is 1, it is P. Okay. Again, when it is 0, it is S. When it is 1, it is P. When it is 2, it is D. Okay, this way. Again, when it is 0, it is S. 1, it is P. 2, it is D. And 3, it is F. Okay, so these are the possible subshells for the corresponding values of L, that is the azimuthal quantum number. Now, the fourth column is we will get the number of subshells. Number of subshells in a shell. In a cell. For the S subshell, number of subshell, it is one only. Okay, one. In the case of this value of L 0 and 1, we'll have 1 over here, 1 over here. So it is 2. Okay. Here it will be 3. Here it will be 4. Okay, these are the number of subshells in a shell. So these are the possible number of subshells present in a principal shell. So for the values of 1, we know 1 subshell. 2 we have 2, 3 we have 3, 4 we have 4. But the possible subshells are S for 1, 0, 2 over here S and P, 3 it is SPD, 4 it is SPDF. Okay, so this was the second information provided to us by the azimuthal quantum number. Now let us do one example over here. Okay, one example, a very simple example. For say, let us say if n is equal to 3, if I write n is equal to 3, principal quantum number, and L it is given to be 0. So what is the subshell? How will you find out? If the principal quantum number is 3 and the azimuthal quantum number is 0, so how will you get the subshell? Which subshell is it? Which subshell? This 3 comes here. For L is equal to 0, which subshell? Tell me. Which orbital, which subshell? For n is equal to 3, L equal to 0, which is the orbital or the subshell? Is it S or P or D or F? For L is equal to 0. When L is equal to 0, which is the orbital I am talking about? Which is the orbital? Yes, I discussed this in the morning class also.
S.
Huh? Look over here.
Yes.
For L is equal to 0, the subshell is S. Are you getting it? That is what I am trying to explain over here. Okay. Now let us go to the answer. For n is equal to 3, this 3 remains here only. And for L is equal to 0, the subshell is S. So answer is 3S. We are talking about the 3S subshell. Another example, if we have n is equal to 3 and say L is equal to 1. So which subshell? It is 3 what? 3 what?
Mm.
3P. Very good. Are you getting the idea now, boys? Are you getting the idea now?
Uh,
Are you getting the try to
yes,
understand the
sir.
Yes,
concept
sir.
over here? Okay. You may read tons and tons of pages on your own, but you will not understand this if you don't try to visualize this concept. Okay, because I am going pretty very slow in this part of the chapter to explain you this concept. Okay. Again, if I take another example, if n is equal to 3, say 4, and value of L is given as, say, let us take 3. So what is the subshell? Right, 4. For L is equal to 3, what is the subshell? For 3. L is equal to 3. For L is equal to
D.
3, yeah, D. Very good, very good. You are getting it. Is it D or F? Just check.
F.
D.
How D? For L is equal to 3, what is
For
the subshell?
3F.
Yeah,
F.
it is 3F. It is F. It is 4F. So 3S subshell. This is 3P subshell. Okay. This is also subshell. This is also subshell. Okay, so these are few examples which will help you get the subshells for the first two quantum numbers. If the first two quantum numbers are known, then we get the subshell to which the electrons belong. Okay, this was the second information provided. Now, moving to the next information. The next information provided by the azimuthal quantum number is, it is called the shape. The shape. The shape of the subshell. The shape of the subshell. Okay. So we come to know about the shape also from the azimuthal quantum number. For example, for a particular given values of L, if the value of L we know it is 0, which is the subshell? Which is the subshell? Tell me. Which is the subshell? For L is equal to 0, which subshell is there? Is it?
S.
Yes, S. So S subshells are generally spherical in shape. I'll come to the diagrams after some time, okay? Are spherical in shape. They are spherical in shape. If you come to L for value 1, then it is P subshell. P subshells are what? They are dumb. Dumbbell. You know dumbbell when you go to the gym, no? We have dumbbells over there, no? Yes? Dumbbell,
Yes, sir.
yes, dumbbell shape. Okay. Similarly, when the value of L is equal to 2, then we have d orbital. D orbitals, they are clubbing of two dumbbells, dumbbells like this. So it is a more complicated shape over here, which is a mixture of two dumbbells or two orbitals from the p orbital. Okay, so that I'll show you the diagrams after some time. Okay, so this is the third information provided by the azimuthal quantum number. It tells us about the shape of the subset. If you know the value of L 0, 1, 2, 3, and so on, then you can figure out what could be the shape of the subset. Now, after this, the next thing I would like to tell you is the fourth information provided by the azimuthal quantum number is, it provides us the the orbital angular momentum, orbital angular momentum of the electron, because electrons are moving in a fashion, they're moving in a fashion, circular fashion, spherical fashion, in a cloud around, like the movement of the earth around the sun, in a somewhat similar, not exactly same, somewhat similar. So from the azimuthal quantum number we get an idea about the orbital angular momentum of the electron. Now, this orbital angular momentum of the electron derivation is not required in class 11 chemistry as such, but they have given a formula to get the value of the orbital angular momentum, which is represented by capital L, that is equal to h by 2 pi, open the bracket, and then L, open the bracket, and then L plus 1. Now this, whatever is inside, everything is under root like this. Everything under root. So this L stands for what? Azimuthal quantum number. Okay. So if you know the azimuthal quantum number, so write it over here, and then H is a constant, Planck's constant, pi is there, pi 3.14, and simplify it, you get the value of the orbital angular momentum of the electron. So these are the four informations which are provided by the azimuthal quantum number. Is this clear, my dear boys? Is this clear to all of you? Is this clear to all of you? Yes,
Yes, yes.
I'm speaking. So azimuthal quantum number L, its value ranges between 0 and n minus 1. So this relationship is important over here. L must be less than or equal to n minus 1. This n stands for principal quantum number, and this over this side L is greater than or equal to 0. So we can have values from 0 to n minus 1. So it provides the following information. Number one is the subshell in which the electron lies. So 0 is S, 1 is P, 2 is D, 3 is F. And after this, the next information provided over here is number 2, the number of subshells present in a principal shell. So for the values of n for a particular principal shell, if the value of n is 1, then the permissible value of L is only 0. So possible subshell is S. So number of subshell is also 1. If you go to principal shell L, value of N is 2. Permissible values of L are two of them, 0 and 1. Possible subshells are S and P. How many subshells? There are two. Are you getting it? There are two subshells. Now, if you try to enter inside this, S will be 1 orbital, P will be 3 orbitals. So 3 plus 1, it will be 4 orbitals. It will be 4 orbitals. If you come down over here, for value of N is equal to 3, permissible values of L are 0, 1, 2. Possible subshells are SP and D. So number of orbitals in this case, where there are 3 subshells, will be 1 over here, 3. 3 plus 1, 4. 4 plus 5, there will be 9 orbitals. 9 orbitals like this. Okay. If you come to value of N is equal to 4, then the permissible values of L are 0, 1, 2 and 3. For 0, 1, 2 and 3, the possible subshells are S, P, D and F. So S orbital is 1, P orbital is 3, D orbital is 5 orbitals, this is 7 orbitals. If you add all this, 7 plus 5 is 12, 13, 14, 15 plus 1, 16. So this is 16 orbitals. This is 16 orbitals. Let me make this picture clear to all of you in the next slide. I'm going to insert one slide over here in between to make the idea of SP and D orbitals clear, okay, with the diagram. Okay, now have a look. S orbital, this is S orbital, then P orbital, P orbital, P orbital, okay, then D orbital, 1, 2, 3, 4 and 5, this is D orbital, and there is F orbital, F orbital, 1, 2, 3, 4, 5, 6 and 7. So these are, S is a subshell, P is a subshell, D is a subshell, F is also a subshell. Okay, now within the subshells we have orbital. These are all orbitals. All orbitals. See, all these are what? Orbitals. All these are orbitals. Are you getting it? All of these are orbitals. Okay, and an orbital. All these are what? Orbitals. All of these are orbitals, and each orbital can accommodate 2 electrons. 2 electrons. How many electrons? 2 electrons. So this is what I wanted to explain you and make it clear to you with the help of this slide. Okay, now this idea is clear. If N is equal to 3 from the example, L is 0, so 3s subshell. If N is equal to 3 and L is 1, for L is equal to 1, the subshell is P, so 3p subshell. For N is equal to 4, L is 3, so 4f subshell. Okay, so after that, the third information provided by the azimuthal quantum number is shape of the subshell. For L is equal to 0, it is S subshell. S subshells are spherical in shape. Okay, P subshells are dumbbell shaped. D subshells are complicated mixture of 2 dumbbells together. And F subshells, they have much more complicated shapes, which is not in the syllabus also for us. Okay, now the next information which was provided by the what you call azimuthal quantum number is called orbital angular momentum of the electron, and I want you all to learn this formula. Please learn this formula. Okay, L is equal to, this L stands for orbital angular momentum of the electron. L is equal to h by 2 pi, open the bracket, under root L, open the bracket, L plus 1, close the bracket. Okay, this is an important formula from which you will be asked simple numericals, where I will give you the value of L, I'll give you the value of H, you know the value of pi, and I'll ask you to calculate without any vertical unit the orbital angular momentum of the electron. Okay, provided I'll give you the units. Okay, now, so 2 quantum numbers have been explained to you. Now, moving to the next quantum number, we have magnetic quantum number, M. It is written ML like this. ML. Okay. L is in the subscript. Now, this magnetic quantum number, it is given. It was solved, and it is mainly to explain the effect of magnetic fields on the shape of the orbitals. Now, The total number of orbitals in a subshell and the orientation of these orbitals are determined by the magnetic quantum number. Just see total number of orbitals, how many orbitals are there in a subshell, and the orientation, which direction they are oriented. Okay, towards the left, right, up, top, bottom. Of these orbitals are determined by whom? By the magnetic quantum number. It is denoted by ml. This number yields the projection of the angular momentum corresponding to the orbital along a given axis. Okay, so if you look at this diagram over here, it will be Greek for you all. Okay, but I'll try to explain it. S orbital is here, S subshell, S orbital, P subshell, P orbital are here, then D over here, dx square minus y square, 5 of them, 1, 2, 3, 4, 5, dx square minus y square, dz square, you have to remember this, dz square, dyz, dxy. Then there are f orbitals, more complicated shapes. You can have imagine it's very complicated. Okay, so these are the shape of orbitals as per the corresponding quantum number. Okay, depending upon which quantum number they are talking about. Now, the value of the magnetic quantum number is dependent on whom? On the value of the azimuthal or orbital angular momentum quantum number. For a given value of L, the value of M ranges between an interval of from minus L to plus L. Value of magnetic quantum number depends upon values between minus L to plus L. Example is given. If n is equal to 4 and L is equal to 3 in an atom, the possible values of magnetic quantum number are L value is 3, so minus 3 to plus 3. So minus 3, minus 2, minus 1, 0, 1, 2, and there is one more 3. So 1, 2, 3, 4, 5, 6, 7, which means it is 7 means it can be 1, 2, 3, 4, 5, 6, and 7 over here. Okay, so I am talking about this f orbital in this example. Okay, now these are the basic things about the magnetic number. Okay, now we move on further in the case of a magnetic quantum number. This, as I've already told you, magnetic quantum number explains. Let me use the next slide and write down over there magnetic quantum number explains the splitting of spectral lines splitting of spectral lines in the presence of magnetic field and that is how we get to know about the idea about the orientation of the orbitals because of this splitting in the presence of magnetic field. Remember, the degeneracy of orbitals is removed. Degeneracy means orbitals which are having the same energy level is removed and they acquire different energies. So that is how it is possible to understand from magnetic quantum number the what do you call the splitting of spectral lines. This splitting of spectral lines, it is called Siemens effect. Zeemans, Siemens effect. Now, to explain this Siemens effect, I will use one more slide to explain the permissible combinations now for principal, uh, azimuthal, and magnetic quantum number in my next slide. Just have some patience. So I'll introduce a slide over here and draw a diagram, a tabular diagram. Principal shell, first column, okay. Then second column I'll write value of n, okay. Third column I'll write down permissible values of L. Then fourth column I'll write down permissible values of M, magnetic quantum number. Okay. Then I'll write down number of subshells, and finally I'll get down to know number of orbitals. So this will complete your concept about the quantum numbers after solving the Schrodinger equation, we get NLM. So these three will be completed by this table. The understanding will be complete by this table. So the first one, principal shell K. I will take K. For K, the value of N it is 1. For K, the value of L is 0. So possible permissible value of M will be, it will be 0, because it ranges from what, 0 to minus L to plus L. So it is only one value over here, 0. Number of subshell, it is S, one only, one orbital, one orbital. Okay, so that completes your principal shell key. Okay, then coming down to the next one, principal shell, let's talk about L. For L, the value of N is 2. Okay, and the permissible values of L are two of them, 0 and another one is 1. Okay, for 0, the permissible values of M will be 0 only, and the number of subshell will be over here, that I'll come later on. For value of L0, the permissible value of M is also 0. Okay, and then over here, for permissible values of L, which is 1, the permissible values of M are three values, minus 1 to plus 1. So minus 1, 0, plus 1. So these are the three values. Okay, and then overall, if I count, the number of subshells will be 2. One is S, one is P, and these orbitals, these subshells are 2s and 2p. Okay, and then if I count the total number of orbitals, it comes to over here 3 over here for p orbitals, px, py, pz, and s is 1. So it is becoming 4. Total number of orbitals is 4. Okay, so this is the total number of permissible combination for the L principal shell. The L principal shell. Okay, now coming down to the next principal shell, M. I write down M over here. Okay, for principal shell M, the value of N, it is 3. So value of N 3 means permissible values of L will be, one is 0, another one is 1, another one is 2. Okay, for 0 it will be 0 only. Okay, for 1 it will be minus 1, 0, plus 1. For 2 it will be plus 2 to minus 2. So I write plus 2, minus 2, okay, minus 2, minus 1, 0, plus 1, plus 2. So you can count 1, 2, 3, 4, and 5 of them. Okay, and then your total number of subshells will be S, P, and D. 3 of them. S, one is P, one is D. 3 of them. And what are those subshells? 3S, 3P, and third one is 3D. So these are the vertical subshells. Now, what is the number of orbital? Let us see. 3S is 1, 3P is 3, 3 plus 1, 4, 4 plus 5 is 9. So here I will have 9 orbitals for the principal shell K, whose value of N is 3. Now similarly, if I go to the last one over here, the principal shell K, L, M, N, for N it will be 4. Permissible values for L when N is equal to 4 will be 0, 1, 2, and one more, that is 3. Okay, so now again similarly, just copy this down. For 0 L0 we have M also one value only, 0. For 1 it will be minus 1, 0, plus 1. For 2 it will be minus 2, minus 1, 0, plus 1, plus 2. For L is equal to 3 we have minus 3 to plus 3, minus 3, minus 2, minus 1, 0, 1, 2, and 3, plus 1, plus 2, and plus 3. So now here you see the orbitals are how many? S, P, D, and F. How many? 4 of them. 4 of them. So the orbitals over here will be, subshell will be 4S, 4P, 4D, and 4F. Now how many orbitals? Let us see. S is 1, P is 3. 3 plus 1, 4. 4 plus 5, 9. 9 plus 7. 9 plus 7 is 16. So we have 16 orbitals over here. So from here you should be able to understand the permissible combinations of N, L, M, principal quantum, what do you call the quantum number. These are the quantum numbers which you are supposed to understand from this table. Okay. Now, can you hear me, all of you? Can you hear me, all of
Yes,
you? Okay, good. Now
yes,
we have how much time left now? 110 to 150. No, okay, so there is time left. Okay. Now
six.
let us move to the next slide. Okay, let us move to the next slide. Have a look at this. It is already prepared before and prepared. Okay, azimuthal quantum number value for 0 s subshell. Okay, it is corresponding number of orbitals to possible values of m is 0. Okay, p subshell, it is 3 orbitals. M values will be minus 1, 0, plus 1. For d subshell, number of orbitals is 5. So 1, 2, 3, 4, and 5. Okay. For f subshell, it is 7. Okay. So here we have 1, 2, minus 3, minus 2, minus 1, 0, 1, 2, and 3. Okay. So this is to give you a brief idea, the concept idea about the permissible combinations of azimuthal quantum number with magnetic quantum number and principal quantum number. Okay, so that chart becomes a very very important chart for all of you. Okay, now have a look at the next and the last quantum number in your syllabus, which is called S, spin quantum number. Okay, it is written by S, spin quantum number. Symbol is like this: spin, clockwise spin, anti-clockwise spin, or plus half, or we write minus half. Okay, like this. Now over here, if you look at the data given over here, the electron spin quantum number is independent of the values of all three n, l, ms. It is independent. So I can ask a question: name the quantum number which is independent of the principal quantum number or the azimuthal quantum number or the magnetic quantum number. So the answer has to be electron spin quantum number. The value of this number gives insight into the direction in which the electron is spinning, whether it is spinning in the clockwise direction or in the anti-clockwise direction, denoted by ms or simply s. ms or simply s. For magnetic, it is what? ml or simply n. Okay, that you should remember. Now, the value of ms offers insight into the direction in which the electron is spinning. The possible values of the electron spin quantum numbers are plus half and minus half. Okay. The positive values of ms implies an upward spin on the electron, which is also called spin up and is denoted by the symbol up arrow. And ms has a negative value. The electron in question is said to have a downward spin or a spin down, which is given by the symbol this down arrow. Okay. The value of the electron spin quantum number determines whether the atom in question has the ability to produce a magnetic field or not. The value of ms can be generalized by plus half or minus half. Okay, so this is the last spin quantum number, which is called spin quantum number. So which completes our understanding of all the quantum numbers: principal quantum number, azimuthal quantum number, magnetic quantum number, and spin quantum number. These three are related to each other, but this one is independent. It is the spin quantum number is independent of the previous quantum numbers. Okay, now we have got very less time left. So in the next class, that means tomorrow, the last period, in the last period, what time is the last period? 1:50 to 2:30. Tomorrow in the afternoon, I will explain you the Hund's rule of maximum multiplicity, which is a very very interesting rule. Okay, so after the Hund's rule, we will learn about some more concepts and then understand, and then later on I'll teach you in this chapter only how to write the electronic configuration also. So I would like to end my class here only, my dear boys, but please hang on over there for some time so that I will record your attendance, and then you can proceed and what you call join the other class. But one information, one notice I want to tell you: those boys who are not regular, those who are not regular at all, that means missing all the classes for the unit test and the upcoming examination this year, I will not correct their answer scripts. Whatever online test I'll be taking, I will not correct it. I'll just save it and send it to the principal, mark as absent for the online live classes. Okay. Only those boys who are regular, one or two classes absent, no problem. But if I'll now compile the attendance in a while, and then I will what do you call, see which boys are irregular quite frequently, and those boys answer scripts I will not evaluate at all. I'll straight away write over there absent. Okay, no evaluation. Okay, so that is the announcement for you all. Hang on over there. Let me take your attendance, and then you can leave and leave this class and join the next class. Okay. Okay. Now I am downloading the attendance list. Okay. It is downloaded. Now you may leave the class. Thank you so much. Have a nice day.